In the last lecture, we were talking about the role water vapor plays in the Indian monsoon. And one thing you must remember, India has a very interesting geography. We are surrounded by Himalayas in the north, and that has a role to play. The Himalayas, which are on this side, very tall, Tibet, which is right here, and Everest and so on, they block the coming of cold, dry air from the mid latitudes. In Sahara, there is no mountain. So, African monsoon does not come as far north as in India because there are no mountains, hence cold dry air from Europe comes into Sahara. Okay. In India, we are lucky, but if you look at the west of 80 east, the mountains are still there. Tibet is not there, other mountains are there, and we have shown that in a climate model, if you remove mountains to the west of 80 east, then the rainfall is affected in India. Because these mountains also, the Karakoram and the mountains in Kashmir, they also stop the coming of cold dry air. So, India is lucky because we have Himalayas to the north, which blocks the coming of cold dry air called advection by meteorologists, and so Indian monsoon is there up to 25 north, while in Sahara it is there up to 15 north. So, we also have to know there is a remote impact of oceans on the Indian monsoon, okay? Not the local land sea contrast in temperature. So, the remote influence comes from the Pacific, the Atlantic, and also the Indian Ocean. Now, the impact of Pacific Ocean Indian monsoon was discovered almost 100 years ago by Sir Gilbert Walker, who connected the oscillations of the pressure near Tahiti in the Pacific Ocean with the Indian monsoon. Okay? And this is called the southern oscillation. There is an oscillation of pressure between Tahiti and Darwin. Darwin is in Australia, Tahiti is in Hawaii, and this oscillation of pressure has an impact on the global climate and weather. Okay? So, this southern oscillation, which occurs in the atmosphere, is influenced by what is happening in the ocean underneath. If the ocean here in the Pacific, the East Pacific, is warm, then the rising air moves here, okay? While at other times when it is cold, it is near Australia. So, the movement of this air between Australia and the East Pacific influences the rainfall over India, and that is a complex relationship between Pacific Ocean and the Indian monsoon. Now, to understand all this, we run climate models now all over the world. We divide the earth into small cubes of various sizes. Okay? This is the typical not cube, but a slightly different shape, and we apply the laws which I just now discussed for a simple model, laws of conservation of energy, of mass, momentum, Newton's law, and also radiation heat transfer, and all these are non-integrated in time. Okay? This is what modern weather forecast models and climate models do. They integrate the equation of momentum, energy, and mass in time and see how the wind moves, how the moisture moves in the world, and how it ultimately releases rainfall in India. So, we discussed these models earlier. There are purely atmospheric models for which you have to provide sea surface temperature, and there are coupled models which solve the equation in the atmosphere and the ocean together in a coupled system and integrated for a long period. Okay? These are more complex models, these are simple models, both are required to understand monsoon. Now, when you look at the prediction of rainfall by these models, of the Indian monsoon, you find this observation of the Indian monsoon around 800 millimeters, 880 millimeters of rainfall in June to September, it varies around year to year 9 to 10%, okay, called the coefficient of variation. Now, this observed mean rainfall and its variability is not simulated by any model. So, models are still having great difficulty in getting the correct mean rainfall and correct variation year to year. Okay. This is a tough challenge. The models have improved a lot in the last 40 years, but still they are not as good as we would like them to be. Okay. So, you can see that there are many models which have very low rainfall and very low variability, and there are models with low rainfall and high variability, and no model comes anywhere near the observation point. More recent information from more recent models. Again, this is the observation mean and variability. No model is able to capture it. Okay. Here, the big dot is average of all the simulation. The small dot is each of the simulation. This is called the ensemble mean. These are each individual simulation. None of them are near the observed rainfall. So, this is the challenge we are still facing. We do not have a single model which correctly reproduces the observed rainfall over India. To show them more clearly, I plotted the various models on this side and the mean rainfall on this side. Okay. And the observed rainfall is around 880 millimeters, and you can see most models are too dry, some of them are too wet. So, no model gets a value around 850, which you should get for the observed rainfall. Okay. Now, here is the seasonal cycle of rainfall as obtained from one of the models, the CAM2, which is the atmospheric model, and CCSM2 is a coupled model. Red is observation. So, when we looked at this model, we saw that the atmospheric model CAM2 had too high rainfall, while the coupled model simulation was closer to observation, and we were quite thrilled. But when I looked into detail, we saw that the coupled model got the right answer because the coupled model sea surface temperature was too low compared to observation. So, in the atmospheric model, we provide the observed sea surface temperature. It rains too much because the way clouds are modeled, it tends to rain too much over India, and that error is partly compensated because in the coupled model the sea surface temperature is too low. So, you have to be careful. This model gets a correct rainfall for the wrong reason. The model has two errors, one error in the atmospheric component, the clouds, the other in the sea surface temperature, and the two errors cancel to give the correct seasonal cycle. So, you have to be very careful. A model can give you the correct seasonal cycle for the wrong reason. So, you have to check both the atmospheric model and the coupled model separately to make sure that model has the right physics. Now, here are some more examples of simulation by various models. Again, black is observation and colors are various models. You can see very few models get the correct seasonal cycle over India. Okay. Most models are too dry, a few models are too wet. Only there is no model which gets the correct shape of the seasonal cycle. So, this is a problem which has not yet been resolved. Here is another example from a more recent model, okay, and green is observation and black is ensemble mean, which is too low compared to observation, and there are some models which are too dry, some which are too wet. Very few models get the correct seasonal cycle. Now, there are a lot of people keep telling me that due to climate change, the seasonal cycle of monsoon has changed. That is not true at the all India level. You look at the all India monsoon rainfall for the 54 years of data here and the subsequent 34 years of data here, and here 24 years, you compare these two, you find that the seasonal cycle is almost same. There are some changes in a few days, but the seasonal cycle rainfall has not changed due to climate change. There may be changes in local regions like Northeast or in Western Ghats or in Rajasthan, but not at the all India level. Now, we are talking about the problems climate models have, but I will give you one good news. You compare the observed rainfall from a satellite, which is known as the TRMM satellite, Tropical Rainfall Measurement Mission, which has a radar in it, compared with the prediction by a model developed in Japan, which has a very high resolution, 7 kilometers, and we see that a 7 kilometer resolution Japanese model gets a spatial pattern of rainfall very close to observation. Now, most of the models today run for IPCC has a spatial resolution of 50 by 50 kilometers. They are much cruder than this model, because remember, this model is run only for a short time, maybe 4 months. If you want to run this model for 100 years, you need a very big computer, which is not there right now. In the next 10 years, it will change. So, although we have shown that models are not doing well over the Indian monsoon region because they are too crude, but these models will improve as the computers become bigger and we are able to run the model at high resolution. The models will simulate the rainfall spatial pattern correctly. Okay? That will happen in the next 10 to 20 years. Now, to show how important resolution is, here I am comparing a heavy rainfall event in the Alpine region of Europe, simulated by a model with a resolution of 12 by 12 kilometers, a model with a resolution of 3 by 3 kilometers, and observation. What do you find? You find the 3 kilometer model gets the short term forecast very accurately compared to 12 kilometers. Okay? So, we need models at the resolution of 3 kilometers to get the high rainfall of the order of 16 millimeters per hour, which is very high. Okay? So, this will happen in the next few years as the computers get more powerful and they run faster. We will be able to run the 3 kilometer resolution model, but today we are not able to do that. Now, I want to highlight this further. If you recall, I talked about a very heavy rainfall event in Uttarakhand in the year June 2013, okay? And it caused huge havoc in Kedarnath where pilgrims had collected. Okay? Now, this shows the simulation of this rainfall. Here the observation is in black, the ensemble mean is in grey, and you see the ensemble mean rainfall at a low resolution whose horizontal resolution around 50 kilometers, it gets only 30 millimeter per day, although it rained more like 120 millimeter. But the same model run at a higher resolution, about 3 times high resolution, is able to get not quite close to the top, but better than this. So, we need high resolution to get the mountains in Uttarakhand correctly in order to get a high rainfall. Okay? So, that is clear that that is going to happen as the models start using high resolution once we have access to a faster computer. Now, the other point made by Hawkins in a paper in Climate Dynamics is that the presence of initial condition uncertainty is always there. The initial condition is now perfectly known. We use satellite data, we use ground observation, but still there is an error. So, it makes significant, irreducible uncertainty in future regional climate change predictions. Okay? So, that is unavoidable. There will be some error because the initial condition is not accurately known. Therefore, if you want to know what will happen in the next 20 years due to climate change, you will not get a reliable answer, because the signal of the impact of climate change will be completely overwhelmed by the noise of internal variation. Okay? So, people who claim to predict the rainfall in the next 10 years are not telling you the truth. It is not possible because of the noise that is there due to internal variability in the model. Okay, so this is a model which was used for this prediction of Kedarnath rainfall. It shows the atmospheric model GFS coupled to an ocean model MOM version 4, and here initial condition being incorporated from atmospheric and oceanic data. Okay. So this model was developed in United States and adopted in India. Now this model's prediction for a 3-day forecast is very good. So today you can trust the model to give a fairly accurate 3-day forecast. Okay. Then if you look at 7-day forecast, which is not bad, but there are some problems. 15-day forecast is improving, but still there are difficulties in predicting heavy rainfall events. 30 days and longer is tough even now. Okay. And that will change as the model resolution improves. Now the reason why models improved dramatically in the last 20 years because of data assimilation, where you combine observation and the forecast to get the true state of the atmosphere. Okay. To get the true state of the atmosphere, we need many observations. We cannot put observation everywhere. So we take the observation both from satellite and ground based stations, and wherever there is no observation, we take the model output as observation and you combine the two. This fusion is very powerful to get the right initial condition. Okay. Now today a typical climate or weather forecast model assimilates a huge amount of data, millions of units, 30 to 50 million units of data from satellite and other ground based radar, radiosonde and other data. So that assimilation of satellite data is increasing exponentially. Now here is the forecast of the all India monsoon rainfall 7 days in advance from the model I mentioned just now. Model prediction is in green and the observation is in blue. You can see that the forecast is pretty good, okay, up to 3 days. After that, slight decrease. It, for example, on day 4, it somewhat predicts lower rainfall than observation, okay, but still the forecast is quite good for up to 7 days. Now, if you connect all this and compare how good is the correlation, well, models at various resolutions here, a coupled model, atmospheric model and coupled model here, and correlation shown here, and these are pentads, 5-day mean forecast. Pentad 1, pentad 2, pentad 3, pentad 4. Pentad 4 is forecast 20 days from now. Okay. Now, if you look at these bars give you the correlation. Correlation is quite good in pentad 1, around 0.8, which is not quite good. It goes down to around 0.6 in the second pentad, that is up to 10 days, and goes down to 0.4 in the third pentad, that is about 15 days, and by 20 days it comes down to 0.3, which is not very good. Okay. So you can see that today's weather forecast is quite good in the first 5 days, it's not bad in the next 5 days, but degrades in the third and the fourth weeks. Okay. And so this will improve as the model resolution goes up. Now the same weather forecast is also used in cyclone forecasting. Okay. In cyclone forecast, the first priority is track forecast. You forecast the track of cyclone, so you decide where will the cyclone land over India. Okay. Now about 15 years back the error was about 140 kilometers, today is less than 100 kilometers, which is a great improvement. Okay? So you can shift people outside the areas where cyclone is going to land. Okay? Where it is landing, the error was around 100 kilometers, now it's around 56. So you move less people around. Okay? So 100 kilometers becomes 50 kilometers. So you are able to predict within 50 kilometers where will the cyclone land. So you can move the people out of that area to surrounding areas for their safety. So cyclone forecast improvement is one of the great achievements of the modern weather forecast models. Okay. Here is an example. I have compared the India Met Department forecast for the seasonal mean June, July, August, September. They claimed it will be between 96 and 104. It was 98, very good forecast. They were not so good for monthly mean. For June they got it wrong, for July they got it slightly wrong, and August was pretty poor. Okay? So the key point is the seasonal mean is good, but monthly forecast still has to improve, although they got it right in September. Now you go to regional part, not all India. It was good over Northwest India and Northeast India, but not over Central India and South India. So you can see that all India seasonal mean is good, monthly mean is not good, regional is good in some places, not so good. All these will improve in the next 10 years because we are going to use a high resolution model in the coming days, coming years. Okay. The main problem we know in all this model is that inability to predict all these cloud features. There are various kinds of clouds during monsoon, the deep clouds, the shallow clouds, the middle clouds, and the ice clouds. All these are not correctly modeled, but their modeling will improve as the model resolution becomes smaller and smaller. Okay? Now we have talked about aerosol and its impact on climate. Now we have to talk about aerosol's impact on monsoons. Okay? Aerosol affect monsoon by altering the amount of radiation scattered to space. Okay? All aerosols cool the surface of the earth. So aerosol should generally cause a decrease in monsoon rainfall, but there is a difference. The salt and sulfate aerosol will cool the atmosphere, but dust and soot, which absorb the solar radiation, will heat the atmosphere. Okay? So the impact of aerosol on monsoon depends on whether aerosol is reflecting or absorbing. So the sulfate aerosols, which reflect sun's radiation, they cool the air temperature, so the atmosphere has less water vapor at low temperature. It makes it more stable and reduces rainfall. So this is happening now. Wherever there is air pollution, sulfate aerosol dominates and the rainfall is low. Now this can be shown through climate models. Here is a forecast, or here is the climate model simulation of the rainfall over the last 140 years. Okay? And you can see that due to greenhouse gases, the rainfall slightly increases. But if you only have aerosol here in black, the rainfall decreases. If you combine the two, rainfall has slightly gone down compared to only greenhouse gases. So you can see that at present the monsoon rainfall decrease in the last decade is primarily due to aerosol, which has more effect than greenhouse gases. But in the future, as the greenhouse gases increase, the greenhouse effect will dominate over the aerosol cooling effect. Here is another paper showing the aerosol effect. This is the total aerosol effect, which is to reduce rainfall. Okay? This is in red here. And if you only include direct effect, that is effect of aerosol on radiant reflected and absorbed, you see India has increase in rainfall. But if you include direct and indirect, that is the effect of aerosol on clouds, which is more important, then India also has a drought. So Right now aerosol is the main reason where Indian rainfall is declining. So, if you impose very strict air pollution control laws in India, the rainfall will actually increase. So, reducing aerosol is important for two reasons. One, it will reduce the impact of air pollution on health, lungs and other things I mentioned. At the same time, it will remove the reflecting component of the aerosol and hence increase the monsoon rainfall. Now, so far you discussed variation day to day, week to week and year to year. Now, we want to know what is the decadal variation of monsoon. Okay. Now, here is the forecast by 6 atmospheric models, that is models which do not have a coupled ocean, but ocean temperature is specified. You see that here in the black is the model ensemble mean, in red is the observation from crew. The climate research unit in East Anglia in England, you see that the model simulation of rainfall is not too good. Okay? It is not able to reproduce the observed variation in red. So, today models are not good for predicting year to year variation. We still have to improve that. But if the same result you take and average it over 10 to 20 years, because of the strong decadal variation of monsoon, because of strong decadal variation of the Atlantic and Pacific Ocean, if you want to simulate the decadal variation, you average the same model data over 10 to 20 years, then your model correctly reproduces the seasonal cycle, the long term change. Okay. So, you can see that the model is good in decadal, but not good in intra-annual variation. Okay. This is a very important result. This is for atmospheric model. The same models you make it coupled, put the ocean, then the simulation is very poor. Okay. This simulation in the black, red is the observation. Coupled model simulations are still very poor. We need to improve the coupled models because they have a cold temperature bias. Now, how was the monsoon in the past? Now, you might ask, why should you worry about it? Now, remember, the models mainly have been trained on the observed rainfall over the last 150 years, for which we have rain gauge data. But that period is not enough. We need longer period data to understand how various changes in the Pacific Ocean, Atlantic Ocean and Indian Ocean affect the monsoon. And so, we need to look at past data. The past data comes from what are called speleotherms. Speleotherms are deposits in the ocean, in the caves, which are called stalagmites and so on. So, you go inside a cave, we see this deposit. They tell you what was the rainfall thousands of years back. So, based on that, we have data for the Indian monsoon going back to 20,000 years, and so that you can use to train a model. Now, if you look at very long time scale of the order of 20,000 years, you find a very good comparison between incoming solar radiation S and the monsoon. This data from China in Donghae Hulu caves, speleotherms, and they show that rainfall variation in the cave is very close to the observed variation in solar radiation at 30 north. So, this is only when you average over 20,000 years cycle. Okay. So, over a long time scale, incoming radiation controls the rainfall. But if you come to not the 20,000 years time, but hundreds of thousand years, then life is more complicated. Both incoming solar radiation and water vapor control Earth climate. If you come to decadal scale, it is solar radiation, water vapor and the particle profile plays a role. So, as you go to smaller scale, more parameters come into play, life becomes more complicated. Okay. Now, here is the global mean temperature over the last 20,000 years. as obtained from proxy data. We saw this earlier, and this was simulated by trace simulation, which we discussed earlier when you're looking at the transition of the Earth's climate from LGM to the present. Okay, and here you see in black is the simulation by the model, and red is the proxy observations. So you can see they are matching not perfectly because proxy data also a problem. So you can see that the model correctly simulates the roll rainfall of 4 mm per day in the last ice age to the present warm period. So the models are able to simulate the changes that occurred in the past, and you can see that due to the fact that the monsoon was influenced by low temperature at the time and lot of ice age effects, but in the last 20,000 years where Earth has been warm, the simulation is quite good. Here is a comparison between simulation and a simple model which I discussed earlier. The simple model relates rainfall evaporation to QNet and water vapor, and you can see all the models are not perfect. It reproduces the variation over 100-year average scale, okay, not year to year but 100-year average. Now you can understand all this, how the greenhouse gases affect the water vapor and the rainfall. So this problem is now well understood, and so it was a combination of proxy data and observation which enabled us to understand what is happening in the past monsoon. Now here is an example of the rainfall simulation in the last 10,000 years. You can see that rainfall has gone down, so has incoming radiation. So this shows clearly the impact of incoming radiation on the rainfall. The rainfall is declining due to decline in incoming radiation. Now this model brings out clearly the fact that the solar radiation variation is very small. In this period, of course, the decline is due to decline in sunlight, but in this region you can match the observation and model only if you include all the components of the model, not just incoming radiation. It include water vapor, vertical integrals, and then you get this result. Okay. So let me conclude by saying that rainfall forecast is good for 3 days. Seasonal forecast is improving but still a challenge. Forecast 1 year ahead is very tough. Decadal variability is simulated by atmospheric model but not by cold models. We know the role of water vapor and incoming radiation. All models predict monsoon rainfall will increase in the 21st century on account of water vapor, but we may have more droughts if aerosol also plays a role. Okay? And the last part, which I might say a few words a little later, is if there is weakening of the Atlantic meridional circulation, then the rainfall may decrease dramatically. That I will discuss in the last lecture in the course. Thank you.